Hey there folks, in this video I'll be showing off exactly, the STM32 based power supply that I've been working on. But before we get started, here is a quick note. Long note, wasn't it? So here is the actual power supply to which I am providing input voltage of 7 volts. Because P-channel MOSFET that I am using can only handle max gate to source voltage of -8 volts. And as for the power supply, it can reach voltages as low as 3 millivolts. And can also go to voltages as high as 24 volts, with max output current of 2 amps. If some of you want to know the output accuracy of the power supply, I got that for you. I've connected the output of the power supply to the multimeter and the load is of 150 ohm. And as you can see, the voltage readings are quite precise. And yes, I calibrated the power supply beforehand. For the folks who want to see the output ripple, here is the output at 7.8 volts. And this is the output at 3.3 volts in buck converter mode. Now if I change coupling to AC and volts per division to 500 millivolts, we can see the noise, and now you must be wondering, well, this is noisy AF. But take a look at the output of my crab bench power supply, which I am using to power this thing. So now you know that the ripple is from the bench power supply. And this is the zoomed in version of the noise. We can clearly see two high frequency oscillations. That was it for the power supply. Now let us take a look at the circuit diagram. Let's start with input supply module, which consists of 3 filter capacitors, 5 volt voltage regulator and another 10 nF capacitor and the output of voltage regulator. Then there are connections to LCD display and potentiometer to set the output voltage. Next, we finally come to our buck boost converter. It starts with a times 11 voltage divider to measure input voltage, followed by a P-channel MOSFET. If you don't happen to have one lying around, you can bootstrap N-channel MOSFET instead. And if you don't know what bootstrapping is, I've already made a video about that. Then we have inductor connected to the drain of P-channel MOSFET and also of N-channel MOSFET. Then Schottky diode is connected in series to stop reverse current. And at the output we have our capacitors and another times 11 voltage divider to measure output voltage. And then finally we have another Schottky diode to complete the circuit when power supply is in buck converter mode. If you forget to use this diode, there will be huge negative spike at the drain which will damage the MOSFET. Now we come to MOSFET driver circuit, which is ultra simple and only requires 470 ohm pull-up resistor and 2N7000 fast switch MOSFET. And as for the software, I've already added comments, but one thing that I will go through is configuring the timers. I'm using timer 1 to turn on and off the MOSFET, and timer 4 to generate interrupt every 500 milliseconds to update the LCD, because we don't want the LCD to get constantly updated and in turn affect our sample rate. To configure the timer, first create an object for class hardware timer. To generate interrupt, set required channel mode to timer output compare. Then set the compare value and finally define interrupt function. Now for our PWM timer, set its pre-scaler to 1 and overflow value to 1000 to generate 48 kHz square wave. That is it for the timers and for this video. But before you go, I want to tell that I'm working on a highest precision $10 multimeter anyone can make. Please do subscribe if you don't want to miss out on that.